quest to find reality on the rocks.
I wanted to find out how the universe really is, to discover the secret plans and hidden schemes behind creation. Why is the whole show the way it is? I wanted to see how much about everything you could cram into one head. This one. I shall begin at the end, as I always do, with my cosmic quest almost over and my head nearly stuffed. The final encounter just a few minutes away. This was the big one. After months of research, I'd come to Cambridge with questions so big about things so big. Only big brains need apply their minds. I was here to meet the big man of everything.
If we do discover a complete theory of everything, it would be the ultimate triumph of human reason. For then we would know the mind of God.
Kiet Vu, Mr. Hawking.
Professor Hawking's ready for you now, Mr. Campbell.
Right, thank you. I had the ultimate questions. Did he have the ultimate answers? Professor Hawking?
At the beginning, the universe contained nothing.
Well, you're not going to get the ultimate answers that easily. First, you have to wrestle with the riddles of space and time, like I had to. After months of struggle, I was even mad enough to weave some of these ideas into a new show.
The theme is that things have happened here, which daren't yet find themselves in the history book.
Could an audience cope with the very beginning? The initial singularity, when we was all just an infinitely small, incredibly heavy dot. Not to mention the very end, the big crunch. I wasn't sure I could.
Does space go on forever? I mean, is the whole thing infinite, or does it maybe come to an end at some place? And is space nothing? Is space nothing? Is there no thing in space, or is maybe the whole thing in some, like almost solid, you know, like packed with gear, but we call it nothing. But in fact, there's a load of stuff that...
It all began with that book. Just like the Bible, we all have a copy and plan to read it one day. Time-reversed arguments show that any Friedman-like expanding universe must have begun with a singularity. One would not specify the position of the moon in terms of miles north and miles west of Piccadilly Circus. Like everyone else I knew, I got stuck on page 27. So I convened a meeting with my mates at the office. Present, Don Wyndham, Tim Fiddler, Campbell in the chair. Agenda, can the mysteries of the universe be solved? I mean, does Hawking claim to know?
No, but I mean, I think...
Have you read it?
Yeah. And I mean, he arrived at this point.
And you can read it?
Calls it the Big Bang singularity, which is sort of like, you know, God said, right, go.
Did he say that it begins a fraction of a second after something? It's like there's nothing, and then there seems to be a fault in the nothing. There's something wrong with the nothing.
Okay, they do, yeah.
There's something wrong with the nothing.
Yeah.
Just a little, wow.
Must have been,
And in actual fact, it's something of infinitely tiny, and suddenly it gets cross with itself.
Well, yeah.
So it can't bear its singularity.
No, it can't, no.
I actually think scientists has come to a point that they're confused themselves and don't know where to go.
See, the trouble with this stuff is you soon lose your grip on it. I couldn't make sense of nothing.
With it all expanding, what's it expanding into?
All I've got is what you see standing in front of you.
What? So the creation of stuff is expanding into nothing. Is expanding into nothing. But is there?
I see, yeah, right.
See what I mean? But is there nothing hanging around here? I mean, is there some nothing here? We can only see the things, you know, and there may be some things we can't see. But then on top of that, there's some nothing. Yeah. Is it? I mean,
Am I entirely something, or is there a load of nothing in me? Meeting adjourned due to nothing. But surely the something came from somewhere. Or has it always been here? Of all my acting chums, I reckoned Big Mac might have the answer. Hey, Mac! Did it begin?
Of course it began. There's a theory, right? It's called the Big Bang Theory. Now, the Big Bang Theory is that if you wind time back all the way, 15 billion years of history will pass you by. You'd see everything go back to where it came from. All the matter in the entire universe would return to a single point, a singularity. This is the very first moment of time and space, the first grain in the cosmic egg timer.
Core, the moment of creation.
Now this is where I get all screwed up, right? Because there was no space. There was absolutely nothing.
Hold on, space was made? I thought space was nothing.
In the zillionth of a second, it was the size of a grapefruit. Okay? Now, in the next 3 minutes and 46 seconds, it expanded to be 10 million miles. Now, to give you some idea of what that's like, stand over there by that wall, and you're going to have to look really closely and carefully at this, okay? Because it's going to happen really fast. But this is sort of how it expanded after that. Kind of like that.
So, what I'm supposed to suppose is there was a bang 15,000 million years ago, and everything, space included, was created, all in one go. It's more than that. This was also the beginning of time. So out of this fault in the nothing came time as well. And from that first moment, the whole universe began to expand, and it's been flying apart ever since.
My theory is that this beginning, this very first instant of the universe being created, is the manifestation of God. Not like some big grandfatherly wrestler in the sky, but like the real God, the God that is the universe. And that we are just cooled down particles of God.
Cool.
More popcorn?
No, thanks.
That's it.
Well, that might have been it, but the blood was up now. How could space and time be created? And what are we doing in the middle of all this? I resolved to phone up a scientist I knew slightly, Jack Cohen. Ah, hello. Is that Professor Cohen? Yeah, Jack, it's Ken Campbell here. Do you remember me from the science fiction festival days? Listen, what I wondered is, can I come and see you? I've got really like a host of questions that I want to ask you. Yeah, well, I mean, I could make it tomorrow. There's a train up to you. I think it's in at you 10:50. Yeah?
Thank you very much, sir.
Great idea. Yeah, is there any chance, Jack, we actually are at the centre of things, just like they used to think?
Well, people used to think it's very tempting to think you're in the middle of things. The problem is that in an expanding universe, where everything is going away from everything else, the whole thing is flying apart.
Yeah, but it doesn't seem that it's going away from us, though.
It does. Whichever direction you look, everything's going away from us.
Yeah.
But I think it's very difficult to imagine, but it's true that if you model that universe, wherever you are, wherever you stand, everything's going away from you. It's like standing on a balloon, and there's patterns on this balloon, and your feet are on the pattern. As somebody's blowing up the balloon, your feet are parting, but also things are getting further away from you, and the further away they are, the more they're going away from you. Now that's true wherever you stand on the balloon. But wherever you stand on the balloon, it seems to you that the rest of the balloon is going away from you fairly uniformly.
Yeah.
And that's just what it's like.
Yeah, but what do you mean to say that the shape of our universe is like a balloon's skin?
The skin is the clever trick. We'll talk about this, I guess, later in the pub.
So the real shape of the universe could be just a few pints away. But would I ever be able to wrap my brain round the dimensions of the universe? Or would I remain stretched across the surface of a balloon?
We're jumped-up chimpanzees. We're jumped-up chimpanzees with this marvellous facility with language. And language was designed for Aggie come into the cave, there's a mammoth out there. And it wasn't at all designed for thinking about what happened early on in the history of the universe.
I soon discovered Jack's friend Ian Stewart is a mathematician.
What we evolved up here for visual sense is very much based on the immediate surroundings in which we live. Three-dimensional space and a little bit of three-dimensional space.
Yeah.
Not really interesting, not bent, straight stuff.
Yeah.
Even when we started to think about the surface of a sphere on which we were living, those senses to some extent fooled people. You look around, it looks flat.
Yeah.
Yeah, I mean the flat Earth model, it's not at all stupid. It worked very well, actually. I mean, it pretty much looks like that.
Yeah. I've always had sympathy for flat earthers. Clearly, when it came to my vision of the universe, I was one. Just as ancient mariners used to believe they could be blown off the edge of the world, so Captain Campbell was adrift in his view of the cosmos. Now, it's pretty weird to think of us all stuck on the surface of this giant ball we call Earth, yet we know it's true. Gravity keeps our feet on the deck. The leap I had to make was to imagine the Earth in a bigger ball we call the universe. But hang on a minute, if the universe was a ball, then where was its middle? Surely that must be the seat of Big Bang. Time to delve under the skin. But presumably there is a centre of it, isn't it? I mean, where did the Big Bang start? It must have a bit where it started?
It doesn't have to be. I mean, again, think of the surface of the Earth.
Yeah.
Wherever you're standing, if you see where you're going, it seems that you go away from you a certain distance, and then eventually things meet up, and about 12,000 miles round either way, you get to the far side. So you're at the middle of it, aren't you, wherever you're standing, because it's the same distance in all directions. But actually it just goes round and round and round, and all points on it are pretty much the same.
Yeah.
So
it's very difficult, though, to
but then you
pick
say,
up...
oh, I see, well, the universe is a skin. It doesn't seem to work.
Okay, now this is...
It works for a moment.
Okay, this is a mathematical point. Okay, our problem is we know too much about spheres. As well as seeing the surface, we know there's a bit inside that they're bent round.
Yeah.
But if you have more complicated multi-dimensional versions of these things, you can set things up so that
all these things happen.
The only thing that's there is the surface. There's nothing inside it, there's nothing outside.
I had obviously underestimated the shape of the universe. It all seemed to work in more dimensions than I thought likely. And apparently bends in directions even Ian can't imagine. Space is bent. Space is curved.
Those can also be bent round, so that if you go off in this direction...
They had a name for this. Curved space. Curved space. That phrase would haunt me.
Bends space-time. And if you've got something and you bend it, then it will curl around the back.
To say that space is curved, you see, that space is curved and then also that time is curved, was for me at the time, I mean, I bought it because it was said with such enthusiasm, such zeal. Time is curved, space is curved. These things, wow, you know, it's like you know, I mean, I don't want to interrupt him too much. But think, well, okay, well, I've learnt this. I've learnt the words.
Obviously, I needed to do some more homework. The reason that space is curved, apparently, is all to do with gravity.
Gravity is not a force like other forces. Rather, it is a
Weird stuff,
consequence.
gravity. We all feel it. But what is it? First, the easy bit, Galileo. With me on Galileo, famous Italian gent who dropped 2 cannonballs from the Leaning Tower. One big one, one little one. Now, you'd think the big one, being heavier, would hit the ground first, but as we all know, they both hit the ground at the same time. More or less. Now, this was the first hint that gravity was not quite what it seemed. Then came Newton, 100 years on, and the apple. This gent mused that while apples in England fall downwards, apples in Australia should fall upwards. So what pulls everything towards the Earth? It all comes down to matter. 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 Newton realised gravity is a force, a pull, generated by matter. But an apple would have to be the size of a planet before you noticed its pull. With me so far? Because the next bit gets tricky. 200 years later, and we get to Einstein. Now, Einstein didn't tell us what gravity did. He told us what it actually is. He posed an ingenious question. Suppose the space we're in is distorted. Would we ever know? Well, of course not, because if we tried to measure a distance with a ruler, the ruler would distort too. The entire framework of our space could be distorting without our knowledge. Rather disturbing, really. Anyway, Einstein said we wouldn't see it, we'd feel it. We'd feel it as gravity. Matter, he said, distorts the space around it, and that's what creates gravity. And there is so much matter in the entirety of space that it shapes the universe. And the theory of relativity proves that space is curved.
Yes.
Does it?
Well, what Einstein said was, if you go up into space,
Yes.
then look through binoculars
Yes.
for ages,
Yes.
you will eventually see the back of your own head.
Really?
The light will hit
You
your
go
head,
along with this, do you?
and it will go right around and go into your eyes.
Yeah. You go along with that?
Oh, yes, yes.
And is there an edge to it?
This is the space.
Yeah.
No.
There's no edge of it.
Well, if there was an edge, what would be over the edge?
Well, I don't know. I don't
Nothing
know.
would be.
Well, how do you know? I mean, anything might be, surely. I mean, you can't say because you don't know that there's something there that therefore there's nothing. Well, what is it, can't you? Say, yeah, it comes to an end, and then there's this stuff.
Well, it wouldn't be full of bricks, would it?
Well, I doubt it. But why not? I can't think why not.
Then what would be over the edge of the bricks?
Well, I don't know.
There's my bus.
It was no good. I just couldn't fold the universe into my brain. No edge. And it's curved so much it comes back on itself.
Welcome to the universe room, where over here is over there, and over there is over here. In this room, down is up, and up, down. Everything is so curved that it's curved in on itself. A finite universe wrapped in a room. Feeling trapped? You can never get out. An impossible shape. This room is your universe. A room without a view. There is no outside, only inside. Welcome to the universe room.
I think I need an astrophysicist to get me out of here. Fisher Dilk's the man. I've decided to ask all the questions, like, why is it the way it is? Is it all going well? Is there a chance it was always here, or does it start at some point? Does it go on forever? If it goes on forever, can it have a shape? This sort of thing.
You really want to find out about the universe?
Yes.
Have a seat.
Thanks.
It's really very difficult thinking about it, because the universe is by definition everything.
Yes.
So one always wants to think about a thing, is you say, well, what else is there? But there isn't anything else beside the universe, because it's by definition the sum of everything.
Yeah.
So you have to think about it in a way that you would not think about any other word. So it seems to me perfectly consistent to say, for example, that the universe might not be infinite, but on the other hand, it might not have an edge.
The universe might not be infinite and might not have an edge.
I don't believe the universe is infinite. Now, what general relativity says is that we live our space is spatially three-dimensional, and it is curved.
But yeah, I mean, but is this so, or is this
Yes,
just
they've done
some
experiments. Yes,
they've done an experiment. They've done an experiment and said, "Oh, we're right. It is curved." But how can you do an experiment that?
Well, there was a very precise experiment which was done, what curved space is the presence nearby of mass.
Fisher told me about this expedition of very English chaps who took a jolly to the small island of Principe, just off Madagascar, and they'd come to take advantage of a total eclipse of the sun. They set up a camera on the end of a very large telescope and waited. Now, although they had a passing interest in the eclipse, they were actually trying to prove that space is curved. When the moon passed in front of the sun and blocked the glare of the sunlight, they were able to take some photos of the distant stars that were just visible round the rim of the sun. These would turn out to be classic snaps. What they found was that the stars just behind the sun appeared to be in different places to normal. The light from the stars had somehow bent round the sun. Could it be gravity exerting its pull? Well, not really, because light doesn't have any mass. So what bent the light? It was space, curved space, just like Einstein said. It caused quite a stir at the time.
What is a scientist? A scientist is an intellectual that works with his or her hands. That's what happened when the modern world started, is that intellectuals, instead of discussing the number of angels on the head of a pin, they started working with their hands. They started building little things on their kitchen tables. They started going off into the shed and fiddling around all day. And they started coming up with all this stuff, which now has taken over the whole world. It's everywhere. All these calculators and computers and machines and aeroplanes and cars and all these things have all come out of that fact of intellectuals working with their hands for a change. So, I mean, I think you should become an intellectual working with your hands. You should start fiddling around, try and do experiments. And then it would be a quest. Then it really would be, I think, exciting. Whereas I think this is angels on the head of a pin time. I could say anything to you. I could say, at the edge of the universe, there are 1 million angels, and they all are wearing golden hats. And how would you know that I was wrong?
Well, that's very much like it is now. Curved space. All right, Fisher, off we go with an astro probe. I got this at a car boot sale. Now, I can't say that I was expecting to see curves in space. Not really. Certainly not the back of my own head. Didn't even expect to see the rest of the universe flying away from us. But despite all that, I did expect to see something. All I saw was the night sky, but just a bit bigger. What Fisher never mentioned is that there ain't a telescope in Britain big enough to see what I was after. Observatorio.
Es observatorio.
Yeah. Yeah. Do you speak English?
No, wie Deutsche.
Deutsche?
Ja.
Ah, good. Ja, bist ein Observatorium, denn, bitte. I was in the Canary Islands to check out this stuff firsthand. My turn for a jolly in the best scientific tradition.
Ich gehe da die erste Klang, the big bang, the großes Knock.
Yeah?
Yeah, the großes Knock. I thought the Canary Islands was like seaside and things like that. It's really all I knew about it. I didn't realise how high the things are. They are so high, you know, these are comparable with Everest and stuff. And then at the top, there's an observatory.
I was here to get some hard evidence. I wanted proof that it did go bang at the beginning, that it is all flying apart. But first I had to find the way in.
Blimey.
OK, Fred, can you bring the telescope down now, please?
The astronomer on duty was Dave Carter.
This is the 4.2-metre William Herschel telescope.
Yeah.
And it's a Cassegrain telescope with a primary mirror.
Is it what telescope?
Cassegrain telescope. A Cassegrain telescope means that the light from the sky, from the star you pointed at, falls on the primary mirror, which will open up now. Fred, can you open the primary mirror now, please? OK.
Yeah.
This is the main mirror of the telescope. Light hits the main mirror, it's reflected back up to a second mirror here.
Yes.
And then down through the hole in the primary mirror, which is surrounded by that black baffle there.
Yeah.
It then goes down to the bottom of the telescope, where the instruments and TV cameras are that we use to examine the light from the stars.
So, where do you put your eye?
Well, you don't use your eye, you use a television camera.
Yeah. And how far can you see?
Well, it's very difficult to determine distances because relativity is a funny thing.
But how near to the edge of the universe can you see?
Well, to objects so distant that light, which is reaching us now, started out 4/5 of the age of the universe ago. So when the universe was only 1/5 the age it is now.
Gee.
And these are the most distant objects we can see.
Well, I mean, could you ever build one that got you right to the edge?
Well, no, because you can never get right to the edge, no. The edge in relativity has no real meaning.
Yeah. So you're looking back into time?
You're looking back into time. As you look at objects with the further away, you're looking back into time, into the history of the universe.
Yeah. Let me just get this right. So when you're looking that far away, it's not just that you're looking far away, you're looking into when it used to be like something else.
Galaxies...
So out there isn't our future at all?
No, it's our past.
Yes.
That's right. And the galaxies that we see...
Is there some sense in which we came from there?
Well, the galaxies we see at that distance look like our galaxy used to. Thousands of millions of years ago.
So we are the furthest in the future that we can ever see, then?
That's right, yes. But you can see to the past.
Yeah.
You can see what things were like in the past. We can't see to us in the past. We can see to galaxies which look now like our galaxy did in the past.
Yeah. Is there anywhere that I can actually see a
galaxy moving away from us? Yes, well, we're going to be measuring some tonight, and why don't you come and help us do it?
Help you? All right.
While we waited for nightfall, Dave's mate on the radio, Fred Watson, began my GCSE in astronomical studies.
When people first started looking through telescopes, they could see things that they could put a name to, stars and planets. But they also saw patches of what they thought was mist in the sky.
Yeah.
And it was not until the early years of this century that the idea that some of these patches were galaxies in themselves, things that were very remote, really came to fruition. We live in a galaxy. We're actually about 2/3 of the way. Let me guide you through to the edge of the universe. The light from our sun takes 8 minutes to get here. But let's imagine going beyond the solar system. The nearest stars are about 4 light years away. These and all the other stars we see belong to our Milky Way galaxy. The nearest galaxy like our own is Andromeda. That's 2 million light years away, and just one of the 100 billion or so other galaxies in the universe. The furthest objects we can see are quasars, and you have to go back 12 billion years to reach them.
What's beyond them?
Nothing. Nothing we can see. The edge of the visible universe is about 15 billion light years away, and this edge is not the edge of space as such. It's really the beginning of time.
I think I've been here before.
Okay, we're going to be looking at a galaxy in the constellation of Cetus, which is here.
Yeah.
Now, this is a chart of the whole of the night sky, the north and the southern half, and we're going to be looking at a galaxy which is just south of the equator. Right. So, if you imagine a piece of sky about the size of my fingernail on this chart, then that's about the size of a print of the Palomar Sky Survey. Now, this is a print of the Palomar Sky Survey, 6 degrees square, and this is our galaxy here. And again, if you imagine a piece of sky about the size of my fingernail now on this print, that's about the field of view of the detector that we're going to be looking at. So if you'd like to sit down, and Neil, if you'd like to go to the object, then we can begin to measure.
We were going to measure how fast this galaxy was flying away from us in the universal expansion plan. This is one of the most powerful telescopes on Earth, and it was my finger on the button.
Oh dear.
Rat action.
So LDSS.
Oh, I put LBSS.
Yes. Yes.
Sorry.
Just start again. Type run space LDSS space 60.
Sorry, well, let's get it right. Run space
LDSS.
Yeah.
Space 60.
Yeah.
Okay, now we're ready to expose now.
Return.
So start the exposure. Right.
And this, Dave, is a galaxy.
That's a galaxy. Okay, now what was
I must admit to being underwhelmed by the view. It could have been tadpoles mating, for all I knew.
Is this to do with it, though, the surrounding?
This is the area of the sky which the...
And yet these few dots on the screen represented a galaxy as big as ours.
Milky Way. You can see it's actually a very distorted shape.
Well, and you can speak confidently about this galaxy, can you, from what's been seen from the telescope and then pipe through into here?
I think this kind of structure is usually associated with this kind of structure here and here is usually associated with galaxies which have recently interacted or merged together. Galaxies collide and merge together, yes.
Oh, really?
Okay, Ken, now I think we can put the grism into the spectrograph and take the spectrum.
Okay. I'll press this return.
Press that return key, that's all we have to do.
This is the prism's now gone into the...
The prism's now gone into the beam, and that disperses the light, separates it out into its various wavelengths.
Now, before we go any further, I'd better rehash Dave's briefing on light. The first bit's simple enough. Light comes in many colours, and the light from galaxies comes in many colours too. This spectrum is produced by the chemical elements burning in each of their stars. The brightest bit is always the blistering hot hydrogen gas. Then it got a bit technical. A colour is a wavelength, you see, a bit like notes in music. Each colour has a certain wavelength, like each note has a certain pitch. For instance, blue light is higher pitch light than red light. We may only see a tiny range of wavelengths, but there's a whole lot more out there. Ultraviolet. X-rays. Anyhow, here's the clever bit. You know when a train passes and goes away, the pitch of the whistle drops? Well, when a galaxy flies away, the pitch of its light shifts towards the red. And when it comes towards you, the light shifts towards the blue. This is the well-known Doppler effect.
Oh, if it's red, it's going away. If it's blue, and if it's blue, it's coming towards you. Very, very little is coming towards us. And there's some sort of, weird little local thing. Basically, the stuff is charging outwards. Anyway, we were looking there with Bob and Fred and Tom and Alex.
And by how much red you can tell how fast
That's right. How much the light has shifted to the red, how much the spectral lines have shifted to the red.
Yeah.
Which we can measure.
And then when you know how fast it's going away from you...
That's right.
You can tell how far away it is
That's correct, yes. If you move the cross with this mouse This is the line, the hydrogen line, the brightest line in the spectrum. We put it on top of the strongest line, the highest peak in that plot. We can measure its wavelength. 6,604.
6,600.
That's 6,604 what?
Angstrom units. An
angstrom unit, which is
a 10 millionth of a millimetre, and that's the wavelength.
A 10 millionth of a millimetre.
A 10 millionth of a millimetre. That's the that's not very big, and that's the wavelength of the light. Now we know that in the laboratory that line has a wavelength of 6,563 angstrom units.
So if we take from 6,600...
Anyway, so they took it away, divided it by itself, multiplied it by the speed of light and a sponge cake, and then I got lost, and suddenly...
The answer, which is 1,874 kilometres per second. Very fast indeed. But slow by galaxy standards.
That's right, yes. A lot of the galaxies that we observe are going away at 10, 20, even 50 times that speed.
Does this measurement have anything to do with the Big Bang?
Well, it does, because after the Big Bang, galaxies were moving away from each other very fast. And the universe expands. Imagine a balloon, and you draw a lot of dots on it, and then you blow it up. Now, what happens to those dots is they all move further and further apart as you blow the balloon up. And the further away they are, the more they increase in the distance, because the whole balloon is expanding.
So we're all on the very edge then?
Well, but you've got to think of it in another dimension, in a fourth dimension, because the universe is a three-dimensional thing. It's not a surface like the surface of the balloon, but there's a fourth dimension in which we're expanding. Imagine it like that. It's very hard to visualise, isn't it?
Well, I don't know. I can do the balloon, then I see.
Yes, that's right.
See, so we're all on the edge. You say, well,
so
no.
Try and visualise something
forget
in
the balloon.
four dimensions, yes.
Slowly it was beginning to dawn what was being said. We are trapped in the three dimensions of space, but there's another one out there of which we're unaware. Now I could imagine what it would be like for a flat being in a two-dimensional paper surface. He could not step out of a prison square because it would enclose his world. He would not understand the concept of depth that comes so easily to us on Channel 4. His only hope of rescue would be for some godlike entity of the three-dimensional world to grab him and place him outside. To him, that would seem like a dimensional jump. Blimey, it's well weird, this world. Maybe my brain's expanded with the universe. A world of impossibilities. Here, normal three-dimensional rules are only part of the story. So when they say the universe began at a point, they mean a point in a higher dimension. So as more and more space is created, the galaxies only appear to move away from each other. But from here, it's obvious. It's not the galaxies that are moving, it's the space that's expanding.
Last the telescope, I can see something through. Wow, wherever you look, what you see is your own eyebrow through. But the cactus plants are gradually getting redder, so I guess they're moving away.
On the horizon is Tenerife, where the final proof of this nonsense lies. High on the lava flows of a still smouldering volcano, they have the ultimate listening post. This is where you come to hear the first echo of the moment of creation.
It's not that impressive on a TV screen. I mean,
it's all.
I mean, it could be anything. It could take it all on trust. Yeah. And then there's the bit where we're into the red shift. So I was expecting to see some red.
Some red?
No, but it wasn't. It was just a longer line. And Dave said, well, you see, the thing is, he knew that was red. That's what that line meant.
But did you believe him?
Well, yeah, I believed him. I believed he was genuine and not a hoax chap.
Well, unlike the telescopes in La Palma, our telescopes can see as far back in time as you can possibly get, right back to within about 500,000 years of the Big Bang.
Yeah.
Now,
well, and there's no further back you could go.
No, you just run into an opaque wall then.
Yeah.
And, well, here it is.
This is it.
Oh.
We say it, there's 3 of them.
Wow.
This is our best one.
This smallest one here is the best.
Really? So yours are sort of wind-up ones?
But it's the same sort of technology that's in your TV satellite dish.
Well, can they listen back to the Big Bang as well then?
If you tune off all that noise and blur on the screen, about 1% of it is this
Big Bang?
Is Big Bang.
Is in fact Big Bang. We do not lie.
Wow. So I'm looking right into the beginning of time.
Well, actually, it's the other way. That way.
Oh, right.
We're picking it up coming from the sky.
Yes.
Bouncing off our mirror here.
Yes.
And it goes in the horn, where we convert it into an electrical signal, which we pick up in the
So is
computer.
this sound that's hitting the
It's
mirror?
not sound.
No.
It's electromagnetic radiation. That's radio, light, heat, the whole shebang.
Right. So what you're measuring here essentially is heat?
It's heat. We're seeing back at this 500,000 years, it was at 3,000 Kelvin. That's about the temperature of a hot coal fire.
So you're receiving 3,000 Kelvin coming in?
Now you've seen the redshift. That makes the temperature 1,000 times less, so it's 3 Kelvin.
It's 3 Kelvin?
It's 3 Kelvin here.
What do you mean if Kelvin? So there was Monsieur Centigrade, Herr Fahrenheit and...
Well, it's just a difference of
Mr. Kelvin.
273 between the two. 3 Kelvin.
Whichever way you look, the heat from the Big Bang beams down.
So why have you got 2 horns?
Well, that's to measure the temperature difference. We got 3 Kelvin, but we're interested in looking at the variations on it. And these 2 horns are looking in 2 different directions. So we immediately get a difference on the sky between these 2 patches of sky.
Right.
You come in and I can show you the actual differences coming in.
Oh wow, you have a shed too. It's not possible that the whole works is carrot-shaped and we're just fooling around on that top bit where the sprouting.
No, it's sort of spherical shape.
Now listen, for I think 9 years, he's been listening to the Big Bang. Yeah? He listen through these things. And I'll tell you what it sounds like. The echo of the Big Bang we're talking about, that's the echo, and it sounds like this.
This is the Big Bang?
This is the Big Bang. Well, if you listen for when the noise is stopped going titter, that is the Big Bang.
Oh.
5% of it is the Big Bang, I have to be honest.
It's quieter than...
It's actually quieter than that. The bulk of it is actually noise within our experiment.
That's the Big Bang then?
Yep, that's the Big Bang.
That was it.
Now, I can make a little demonstration to prove that we're actually listening, if I can borrow your hat. Roger, could you be good enough to put that in front of one of the horns?
If you do not mind.
You're putting that in front of one horn?
Just one horn. Okay, now.
Wow! That's my hat. That's the sound of my hat.
What's happening is your hat, which is at room temperature, is in front of one horn.
Yeah.
You've got the CMB coming in the other horn at 3 Kelvin.
So there's a difference of a factor of 100 between the two.
Yeah.
That's why
Your
we get
hand
such
could
a...
make so much difference.
Does this ever change?
Yep.
How many years have you been listening to this?
Oh, about 10 years.
Really?
So his job is to clear it of impurities. So they record the echo of the Big Bang up there, and then they clear it of impurities. What, I said, what do you mean? So it's all the same? Yes, he said, exactly. You know, so it's one exact... I said, blimey. I said, oh, then what do you do with it? Ah! He said, then we look for the differences.
What we're trying to do is actually make a little map with the variations in temperature.
Yeah.
Which will be a map of the primeval gas.
Yeah.
This gas map shows the ripples in the fabric of space-time that gave rise to the clusters of galaxies we see today. And I was told that that's as far as anyone can get. Ken Campbell had almost reached the edge. Before I left for home, there was just one more thing I needed to ask Fred and Dave. If this universe is so enormous, surely we can't be the only ones in it.
I mean, we're here, we're on a planet going around a particular star. In our galaxy, there are 10,000 million of those stars at least. Any one of whom could have planets.
But if there is any, what we call intelligent life is only ever on those bits of scum, as you call it.
Well, it's the debris left over.
The debris left over.
From the formation of a star.
Yeah.
That's right.
As we understand it, life depends on complexity, I think. And complexity has to really come out of the heavy chemical elements. And the universe is mostly fairly light elements, hydrogen and helium, and that's almost all the universe is those elements. And the planets just happen to be where the heavy elements are concentrated.
The universe has to get to its present state before you can expect to see life. And in our particular case...
But there could have been life before ours.
But not necessarily, because perhaps the abundances of these heavier elements wouldn't have been around in the universe. I mean, in space generally, we are the product of a cloud of gas that collapsed and formed the sun.
Yeah.
But there have been previous generations of stars which have enriched space with these heavier atoms that form the bits
and what you call the impurities,
which form an important part of our makeup.
Yeah.
So that was it. First, the incredibly hot bang, the creation of time, space, and every single particle of matter, all in one go. And as the universe inflated, expanding at an unreasonable speed, it began to cool off, from trillions of degrees to a couple of thousand, taking 500,000 years to do it. And as the heat haze cleared from the initial phase of creation, it left ripples in the hot gas that gravity would fashion into the swarms of galaxies we see today. But not for another 3 billion years. In the gravity crush, the first stars were born. Nuclear engines that cook hydrogen gas into all the heavier elements, including the carbon and stuff that make us up. All stars get old and die. And when they do, they scatter these elements out into the great walls of dust. Like the one that formed our solar system 5 billion years ago. Out of this debris, gravity spins a new star and a few scummy planets. Earth happened to be in the first batch of planets laid by the cosmic egg. And it was just the right distance from the sun so that in the primeval chemical soup of the sea, life could emerge. Simple at first, of course, but about 1 billion years ago, complex creatures crawled onto the land. The game of survival drove a chain of evolution to produce all sorts of animals. Some lost out. Others got lucky. We were truly born in the Big Bang. Our bodies made of the dust from long dead stars. We got here just as soon as we could. So that was it. 15 billion years downloaded from the Campbell's brain in 2 minutes flat. But there's one thing I still couldn't see. How everything came from nothing.
Next week, Ken Campbell goes underground to investigate the true nature of nothing at the world's largest experiment in Switzerland. That's at the same time, 8 o'clock.